Now, if we plot the potential, what do we get? So I guess we need to know what this is hooked up to. Let's hook it up to a battery. And we'll make that, what do you want to make that? 12-volt battery? So how are you going to plot the potential? Over here? And what should we call that? How many volts? 12 volts. Then where do we end up? And this one has to be 0. And that's going to be linear. Because we have this relationship, the electric field multiplied by the distance is negative delta V, or E equals negative of delta V over delta S. So the electric field's constant. As we multiply by the distance, it increases, right? The potential increases, I should say. Let's think about if we stuck a charge. If we stuck a charge somewhere in those plates, let's say we put a positive charge in here somewhere. If we put it close to the negative plate, does it have a lot of potential energy or a little bit of potential energy? Positive charge. Yeah, what is it? Which way is it going to go? Positive charge. It's going to go to the right. So does it have very far to go? No, it's like holding something right over the table and saying, I'm going to let go of it, right? How much energy does it have right here? Not much, right? It's not going to get going very fast before it hits the table. This charge is not going to go very fast before it hits something. So it doesn't have very much energy. But you put it all the way over here and let go of it. Now it has a lot of potential energy over here because it has a long way to go. When it hits the wall on this side, it's going to be going fast. You see that? So what is potential energy? It's Q times the potential, right? Q delta V. So let's look at this. We would expect our positive charge to have the most potential energy when it's close to the positive plate and the least when it's close to the negative plate. And so this slope kind of makes sense because if we multiply this by a positive constant, if we multiply this by Q naught, a positive charge, we just get a different straight line with a slightly different slope. Biggest potential energy on this side, 0 on that side. So the potential should have that same shape to it. Does that make some sense? Because if we multiply this by Q, we get potential energy. And if we multiply it by a negative Q, what happens? It flips. It has the most potential energy when it's closest to the negative plate because a negative charge, if you put a negative charge in here and you released it from the negative plate, it would have a really long way to go before it hit the wall on this side. If you released it from here, it would hardly move at all before it hits the wall. So a negative charge has the greatest potential energy on this side. So let's just draw those in now. If this is our potential and we want to draw U, this would be, now we're getting into 21, which is current, DC circuits, things like that. Why are we doing this? It's all around us. right? We use circuits for everything. All kinds of things that we use to make our lives easier. Computers make our lives easier for the most part, right? Especially if you had to perform some kind of a repetitive task, right? If you wanted to do some calculation a whole bunch of times, you'd be desperate for your computer, wouldn't you, if it was taken away from you? So they make our lives easier. And all of our appliances at home, our clothes washers and dishwashers and things like that, things that make our lives easier. They run on electronic circuits, right? Electronic circuits that run them. Even the simplest device, the toaster, is such a simple device. I looked at my toaster at home. It says it has a computer chip inside of it. I don't know why a toaster needs a computer chip, but everything these days, right? Medical applications, defibrillators, pacemakers, all kinds of diagnostic techniques use these techniques of DC circuits and electrical currents. I know that there's one for measuring body fat even, right, where they hook up some electrodes and they kind of measure your body resistance and they determine your percentage of body fat from that. I'm not sure how accurate that is, but anyway, all kinds of techniques and applications in medicine. And just, all around us, things that enrich our lives like communications and entertainment devices run on circuits. Our houses filled with electrical circuits because our devices all run on electricity. And so that's what we're going to spend a little bit of time with now. Before we get too heavy into this, let's just talk about some of the symbols that we use. The first one is our power source for a DC circuit. DC stands for direct current, and that means this is a DC power source. Direct current. So the current always flows in the same direction. This is a sort of a constant voltage power source, like a battery. A battery, like in your car, it's a 12-volt battery. Always puts out the same 12 volts. Current flows in one direction from the positive terminal to the negative terminal. Whatever it is, your battery, any battery in any of your devices, mobile devices, constant voltage source. The current flows from the positive terminal to the negative terminal, a DC power source, batteries. An AC power source, we draw it sort of like a little sine wave in here because that's what's happening to the voltage. It is varying like a sine wave, up and down, up and down. At some instant in time, the left side of your power supply has positive voltage, and the right side is negative. The current is flowing from the positive side through your circuit to the negative side, and then the voltage switches. It goes through zero, and it goes negative, where this side would be negative and this side would be positive, and the current's flowing the opposite direction. It alternates. It's AC, stands for alternating current. That's what's coming out of our walls. AC. So most of the devices, anything that plugs in, is designed to run off of AC power. We're going to focus on DC power. And then we have some devices we have to deal with. We have resistors, and we draw them like that. And we already talked about capacitors, and you know how we draw those. We draw the little parallel plates because that's a very common type of capacitor. I guess I should tell you that these lines we draw are perfect conductors. They have no resistance. When we draw lines in circuits, we assume that those lines have no resistance. If we need to account for the resistance in a wire, we add the symbol for a resistor and we put the value there, it's equal to the resistance of the wire. The lines are perfect conductors. And what else? Is that it for now? We'll add to this later as we learn more devices. We'll learn about inductors and things soon. But right now, I think this is a good start. Okay, a couple of terms. EMF we see a lot. It's sort of an antiquated term. We don't really use it anymore. Originally it stood for electromotive force, and I don't think a lot of books don't even call it that anymore. They just call it EMF. It's the maximum output, it's the maximum potential of a device. So like a battery, that's labeled 12 volts, your car battery maybe. The maximum it can put out is 12 volts. We'll talk about why it might not put out 12 volts. But if it's labeled 12 volts, then that's the EMF. Okay, might be less due to the current flow. We'll talk about that later.